Welcome to a new chapter, namely shear stress in beams. We shall look at the general formula for finding shear stress in various horizontal layers across a beam's cross-section in this lecture. Before we actually begin to understand the concepts related to shear stress in beams, let us briefly recall the scope of the present chapter in the broader subject of machine design. The failure of a part or member is judged either by stress or by deformation exceeding the respective permissible limits with suitable margin or factor of safety considered. The failure due to stress is classified into normal stress and tangential stress with reference to the area on which the stress acts. The normal stress can be further classified by the direct stress, where the resultant of the force vectors pass through the centroid of the section, and the bending stress, both of which can be either tensile or compressive in nature. The tangential stress is also called shear stress and is classified into direct shear, shear due to bending, and torsional shear. As a designer, we aim to ensure that the induced stresses always remain within the permissible safe design or working stress, which is given by the actual failure stress, that is the yield stress in ductile material or the ultimate stress in brittle material, over the margin or factor of safety. In chapter 2 of this course, we found out the maximum shear force and bending moment developed in beams. Further, we used this value of the maximum bending moment to calculate the induced bending stress in the last chapter, that is chapter 3. The maximum shear force as calculated in chapter 2 is now considered to find out the maximum shear stress setup in beams. Down the line, in the subject of machine design, if either the induced bending or induced shear stress exceeds the respective permissible limits, the dimensions or the area of the part or member are suitably increased or the material upgraded as a part of the general design procedure. Now, the shear force and the bending moment in a beam vary in value from section to section. Due to the shear force, shear stresses are set up across transverse or cross sections of the beam. The transverse shear stress produces a complementary horizontal shear stress acting on horizontal layers of the beam. In this chapter, the distribution of shear stress on different horizontal layers across a cross section carrying maximum shear force is determined. Standard shapes such as rectangular, circular, and triangular sections are initially considered, followed by composite shaped sections. Note that the concept of shear flow or shear center is not considered in the present course as it is beyond the scope of the syllabus. Let us now derive the general formula to find the shear stress at various horizontal layers across a beam's cross-section. Let an arbitrary cross-section AB of a part of the beam with length del x carry bending moment m as shown. At the cross-section CD, because of the variation of the bending moment from section to section, the moment is denoted as m plus del m. We show an arbitrary layer at distance y1 above the neutral axis. An isometric view of the differential beam is also drawn for ease of visualization. The width of the beam is denoted by B. An elemental cylinder of cross-section del A is shown acting above the arbitrary layer EF in the plane AB at a distance of y from the neutral axis. Now, I is the area moment of inertia of the complete section above the neutral axis as usual. It is required to estimate the shear stress on section AB on a layer EF at a distance of y1 from the neutral axis. The bending stress intensity on section AB acting perpendicular to the cross section is given by sigma, while for section CD it is given by sigma plus del sigma due to a change in the bending moment. Now, the bending stress for the elemental cylinder at section AB is given by m over I times y. Similarly, the bending stress for the elemental cylinder at section CD is given by m plus del m over I times y. The normal force for the elemental cylinder at plane AB is given by the bending stress times the differential area del A, which is m over I times y times del A. Similarly, for plane CD, the value changes to m plus del m over I times y times del A. Hence, the net unbalanced normal force on the elemental cylinder is found to be del m over I times y times del A. For the complete area above the layer EF and between sections AB and CD, total unbalanced force equals area integral of dm over I times y times dA. dm over I can be taken outside the integral as they are constants here. Hence, the unbalanced normal force acting over the layer EF between the sections AB and CD is given by dm over I times the area integral of y times dA, or dm over I times A times y bar. Let us treat this equation as 1. Now, the horizontal section of the beam at level EF must offer a shear resistance for avoiding the failure due to shear by the net unbalanced force, which we may refer to as the horizontal shear force, given by dm over I times A y bar. The resistance shear force offered by the horizontal section is tau times A, where tau is the shear stress and A is given by width B times dx. Let's denote this as equation 2. Equating both the equations, we have tau equal to dm over dx times ay bar over bi. From chapter 2, it is learned that the rate of change of bending moment with respect to the length at a section equals the shear force at the section of the beam. Hence, the shear stress tau for an arbitrary layer is generalized as S A y bar over bi, where S is the maximum shear force at some location along the beam's length. Here, it is important to note that A is not the complete area of cross section of the beam, but instead it is the area of the cross section above the arbitrary layer EF. AY bar should be taken as a combined term defined as the moment of the area above the arbitrary layer with respect to the neutral axis. B is the actual width of the arbitrary layer, that is at the layer EF. In the next lecture, we shall use the general shear stress formula to calculate the shear stress at various horizontal layers and plot the shear stress distribution diagram for a rectangular section.